Today I'll present our work, a bias-aware computational framework for drug and compound prioritization across neurodegenerative diseases. As we all know, in silico drug repurposing using gene overlap analysis is a fast, low-cost way to screen candidate treatments for Alzheimer's, Parkinson's, and ALS. But there's a critical flaw in traditional scoring methods, which is the core motivation of our study. Let me walk you through our research step by step on this poster. So first, let's look at the left column of the poster. Traditional gene intersection drug screening relies on shared genes between drugs and disease pathways. However, broadly annotated pleiotropic genes such as TNF and IL-6, which link to hundreds of human diseases, artificially inflate matching scores. Drugs targeting these common inflammatory genes are falsely ranked high, even if they lack disease-specific therapeutic potential. No existing pipeline corrects this annotation breadth bias, which creates unreliable candidate rankings. From this gap, we raise our core research question: what is the relationship between gene annotation breadth and drug ranking inflation? And can we correct this bias to improve the clinical reliability of drug screening results? We put forward a clear hypothesis. If we assign lower weights to widely annotated genes, we can reduce artificial ranking inflation and generate candidate drug lists that better match real clinical trial evidence. In the methods, our bias-aware workflow has 4 key modules. First, data preparation. We integrated 2 well-established public datasets, clean DG-IDB drug target intersection data and open target disease gene association. We only kept drug disease pairs that share at least one gene, resulting in a total of 62,887 valid pairs across 3 degenerative diseases. Second, our core bias corrected scoring algorithm. We calculated raw gene overlap scores, then applied gene-specific weights to panelize broadly annotated genes, generating adjusted corrected scores and a breadth and attenuation coefficient to quantify bias magnitude. Third, matched null permutation robustness testing. For the top 200 highest scoring candidates per disease, we ran 500 random target sets permutations, matching original targets counts and gene annotation range. We output in periodical Z and Q values to test if high scores outperform random baselines. Finally, 2 independent validation strategies. We benchmark both raw and corrected rankings against clinicaltrials.gov clinical records, plus a manually curated therapeutic benchmark dataset with labeled effective and failed drugs. We used ROC, ALK, correction, correlation, and top K recall as evaluation metrics. Now let's focus on our key results, shown in Figure 2, 3, and 5 at the bottom of the poster. First, Figure 2 shows the global impact of annotation correction. Over 99.7% of all drug disease pairs has drastically reduced scores after weighting. The distribution of attenuation coefficient confirms that pleiotropic inflammatory genes are the primary driver of the artificial score inflation. Second, Figure 3 visualizes the rank shifts after correction. The median drug ranking changed by more than 900 position. Mainly previously top-ranked compounds dropped thousands of spots, almost entirely because their targets were overly broad disease-associated genes. This proves our method successfully reshapes candidate priority lists and removes bias from widely studied genes. However, our clinical validation delivered a counterintuitive finding. Noted on the right side of the poster, correction fails to improve clinical trial alignments. As shown in our supplementary clinical plots, both raw and corrected scores produce near random ROC-ALK values close to 0.5, meaning neither scoring version can reliably distinguish drugs with advanced phase 2 plus clinical trial evidence. We further validated performance on our curated therapeutic benchmark in Figure 5. Surprisingly, the original uncorrected raw score outperformed our bias-corrected score in ROC-ALK and average precisions. Even candidate-rated highly bias-adjusted frameworks still include compounds that failed late-stage clinical trials. To summarize the discussion, while we successfully eliminated annotation breadth bias mathematically, this correction does not translate to better alignment with real-world clinical outcomes. The broad, non-specific inflammatory genes panelized in our model still play functional roles in neurodegeneration, so downweighting them weakens our ability to recover proven effective treatments. Let's wrap up with our conclusions on the far right of the poster. We successfully built a fully bias-aware computational framework to prioritize drugs for Alzheimer's, Parkinson's, and ALS. Our gene weight correction effectively weakens the overrepresentation of broadly annotated genes and dramatically rearranges drug rankings. Crucially, this bias correction does not consistently improve downstream clinical trial matching. Therefore, we do not recommend this tool as a predictor of clinical drug efficacy. Instead, its appropriate use case is transparent early-stage hypothesis generation and preliminary candidate triage for follow-up wet lab testing. In future work, we plan to integrate tissue-specific gene expression data to refine our gene weighting strategy and test multi-omics feature combinations to boost clinical predictive power.